In this section, you'll learn how to capture data from a game running on a connected Android device and how to generate and analyse a Performance Advisor report. Performance Advisor provides the easiest path to start analysing your game and can be used by your whole team on a regular basis to spot trends and diagnose problems early in the development cycle when you're best placed to do something about it. With Performance Advisor, you get a quick summary of game performance, which can be useful as a daily health check. It's quick and simple to generate a report, particularly if you build it into a continuous integration workflow alongside your nightly build system. The reports contain easy-to-read interactive charts showing you how FPS changes over time and where the device is struggling to process CPU or GPU workloads. We can see the number of draw calls, vertices, primitives and pixels that were processed per frame, shown alongside the FPS and any content budgets we decide to set. You can capture images of slow frames so you can see what was happening on screen when the frame rate dropped. If you can correlate frame rate drops with peaks in CPU, GPU or content activity, you can prioritise these areas for optimisation. Let's take a look at the tool in action. Performance Advisor generates a report from a Streamline Capture file, so the first step is to take a Streamline Capture of your application running on a connected Android device. But in order to capture the extra frame data from the device that Performance Advisor needs, you must run the Python script lwi_me, which is located in your ARM Mobile Studio installation directory. On macOS, there's a launcher file here that will open the terminal app and add the PA command to your path. Go to the Helpers directory where the script is located. The command to run the script is simple. This is all you need. But we can also pass options to the script to control how it runs. This option tells Performance Advisor to capture images of frames when the FPS drops below a default of 30. And here we are telling Performance Advisor where to save those images. The script identifies the device and returns a list of the debuggable applications installed. Enter the number of the app you want to analyse. The script connects your device to Streamline and returns the next steps you should take. Open Streamline and you should see your connected device and a list of the applications installed on it. We can only profile debuggable apps, so use this setting to narrow down the list. Choose the app you want to profile, and then select Configure Counters. Let's use a template to select the best range of performance counters for the GPU in our device. You can specify further settings, such as the sample rate and how long we want the capture to be. Let's capture the first 2 minutes of the game. Now we can start the capture. Specify the name and location of the capture file that Streamline will create when the capture completes. The app starts automatically and we can run the test case. The charts show the hardware counter activity being captured from the device. After 2 minutes, the capture will stop and the app on the device will exit. We'll look at the Streamline Capture later, but for now, let's generate a performance report from this data with Performance Advisor. Back in the terminal, press Enter to stop the script. Any captured frames from FPS drops below 30 are saved as images to the folder you specified earlier. Next, we will run the PA command on the Streamline Capture file to generate the performance report. This command also takes a number of options, and you can create a simple text file to easily pass those options to it. We've added a name and timestamp for this build, along with the application name and the device we are running it on. This tells Performance Advisor to calculate the charts and advice based on 30 FPS as our target performance. This will add our slow frame capture images to the report. And here, we've supplied a set of performance budgets for this device, which will be shown on the charts, making it easier to spot problems. Run the PA command on the Streamline Capture file and specify the file containing the options. The report is saved as an HTML file to the current location. Let's open the file and take a look at the report. The first part of the report shows a summary of how the game performed. We can see the average FPS, a breakdown of workload, and the average utilization of the CPU and the GPU in the device. In this 2-minute section of the game, we only achieve 30 FPS for 4% of the time. For the frames that are below target, the game is fragment bound. This means that the GPU in the device is struggling to process fragment workloads during the pixel processing stage. This could be because there's too much fragment work to do, or that the fragments are not being processed efficiently. The report links out to optimization advice about what you can do to improve fragment-bound content. Here we can see how the game performed on the device over time. The game starts off performing well, although this section is just the loading screen. Then, as the action starts, performance drops, and it stays that way throughout. The background colour of the chart tells us which workload is causing the problem. To provide some context, we added annotations to this game to label different regions in the scene. Selecting a region filters all the charts to show you information for just that region, so if you know your problem lies in a specific area, it's easy to focus on it. These markers show where the frame rate dropped below 30 FPS and a frame is captured. Looking at these images helps us to identify which content might be causing the problem. Because the FPS stays low throughout, Performance Advisor takes a screenshot every 200 frames. This is the default setting, but you can change it to any number. Here we can see how the number of CPU and GPU cycles per frame changes over the duration of the scene. Each chart also shows the frame rate, so you can look for areas of correlation that might indicate a problem. On the GPU cycles per frame chart, we added a budget for this device of 28 million cycles per frame. We estimated that this is the maximum number of cycles that this device should be able to handle, while still achieving a frame rate of 30 FPS. The GPU demands of the game significantly exceeds this budget, and the number of cycles increases over time. Looking at shader cycles, we can see that the number of execution engine cycles is high. Inside a Mali shader core, the execution engine is responsible for processing arithmetic operations. Performance Advisor flags this as a problem and advises us to reduce computation in shaders. You can do this by reducing the precision of shader variables to medium P rather than high P, or by reducing the game's rendering resolution. Draw calls are expensive for the CPU to process, and here we can see that the number increases over time, well above our budget for this device. We should aim to reduce the number of draw calls by batching objects into single draws and discarding those that have no visible impact on the scene. Ideally, the ratio of vertices to primitives should be close to 1:1, meaning that on average each vertex is used by 3 primitives. If there are many more vertices than primitives, the object meshes used in the game could be improved by identifying shared vertices and using an efficient indexing method to order them. For primitives, we can see the total number processed and also the number that were actually visible on screen. We expect around half of the total number to be discarded due to primitives that are in frustum but back-facing. Here we can see that more than half of the total primitives are being discarded. We'll need to check Streamline to see why, as there could be opportunity to optimise here. To stay within our power budget, we can monitor the distribution of GPU bandwidth and the breakdown between external reads and writes. Even if the device can handle the memory demands of the game, we must try to minimise external memory accesses to reduce energy consumption, freeing up power budget for use elsewhere. You can also see the amount of overdraw per pixel, so you can identify areas to optimise. If content has high overdraw, it can perform poorly because of the cumulative cost of shading multiple layers. Common problem areas for overdraw are user interface elements that hide complex objects that were already drawn behind them, or 2D games that use many layers to create a 3D effect. You can use Graphics Analyzer to further explore overdraw and find layers that could be discarded because they have no visible impact. Because we added regions to this game, the rest of the report presents the same charts again, broken down by each region. So in this example, Performance Advisor told us that most of the poorly performing content was fragment bound, and it identified high computation in shaders. But how can we reduce the fragment workload to a level that this device can handle? Streamline will tell us more about how the GPU handled this heavy fragment workload, and we may find more clues as to what we can do to lighten the load. For more videos in this series, and for more information about ARM Mobile Studio, visit the ARM Developer website.